Hi, everybody. It's Professor Mitchell. Today we are starting Chapter 10 on correlation and regression. We're only going to cover just these first two sections. So in this section, we're covering correlation. We introduced linear correlation coefficient, R, which is a number that measures how well paired sample data fit a straight line pattern when graphed. And you'll see a lot of pictures of this in a little bit. We use the sample of paired data, sometimes called bivariate data, to find the value of R. And then we use R to decide whether there is a linear correlation between the two variables. We are only considering linear relationships, which means that when graphed in a scatter plot, the points approximate a straight line pattern. Then we discuss methods for conducting a formal hypothesis test that can be used to decide whether there is a linear correlation between all population values for the two variables. So when we talk about correlation, a correlation exists between two variables when the values of one variable are somehow associated with the values of the other variable. A linear correlation exists between the two variables when there is a correlation and the plotted points of paired data result in a pattern that can be approximated by a straight line. So here's an example. These two pairs of data, or these two variables, show a distinct straight line or linear pattern. We say that there is a positive linear correlation between X and Y, since as the X values increase, the corresponding Y values also increase. So if you think back to your algebra and finding the slope of a line, remember that if the line goes up as you look from left to right, that line has a positive slope. So in the next section, 10.2, we're going to be talking about how to find the equation of this line, which you can use to make predictions, right? If you have a particular value of X, what would be the predicted value of Y from this so-called line of best fit? Okay, just finding my mouse here. There we go. All right, on the other hand, this would be an example of a negative correlation. We see a distinct straight line or linear pattern, and we say that there is a negative linear correlation between X and Y, since as the X values increase, the Y values decrease. If you were to put a straight line over this scatter plot, that straight line would have a negative slope. So again, in the next section, we'll talk about how to find the equation of that line. All right, here's an example of no linear correlation. There is no distinct pattern, which suggests that there is no correlation between X and Y. All right, and here's another example. There is a distinct pattern suggesting a correlation between X and Y, but the pattern is not that of a straight line. This would be an example of a quadratic correlation. Again, thinking back to your days in algebra, these points look like they lie along a parabola. All right, we use the linear correlation coefficient R, which is a number that measures the strength of the linear association between the two variables. So I'm happy to have this picture back because these numbers were underneath the pictures that we were just looking at, but I didn't really talk, well, I didn't talk about them at all. So as you'll find out here in a little bit, this value of R is always between -1 and 1. And the closer it is to -1 or 1, the stronger the linear relationship is. So in this example, you see that R is 0.859. So that's pretty close to 1. That suggests a pretty strong positive linear correlation. This one is even closer to -1. So this is a very strong negative linear correlation. This one here is close to 0. All right, so when you have a value of R that's close to 0, that suggests no correlation. Also, this one here, this value of R would have been calculated using the linear, the formula for the linear correlation coefficient. So even though this is it's really a perfect quadratic correlation, that is not a very strong value of R, okay? All right, the linear correlation coefficient R measures the strength of the linear correlation between the paired quantitative X values and Y values in a sample. All right, so the objective in this section, or in this part of this section, is to determine whether there is a linear correlation between two variables. All right, so we've got a formula coming up here. This is going to remind you a little bit of your formula to find standard deviation. So remember that N, well, in this case, N would be the number of pairs of sample data. This capital sigma denotes addition. Sigma X means the sum of all the X values. Sigma X squared indicates that each X value should be squared, and then those squares should be added. And compare that to the square of the sum of X, which indicates that the X value should be added and the total then squared, all right? And again, you had to calculate both of these things way back in chapter 3 when we calculated standard deviation. Okay, so you've got a lot of practice with avoiding confusion between those two things. All right, and finally, the sum of X times Y indicates that each X value should first be multiplied by its corresponding Y value. And after obtaining all such products, find their sum. R is then the linear correlation coefficient for sample data. And this is the lowercase Greek letter rho, R-H-O. Kind of looks like a P, but it's really the Greek equivalent of R. That is the linear correlation coefficient for a population of paired data. Remember, we sort of have a tradition of using regular letters for sample data and Greek letters for population data. About linear correlation in the corresponding population of paired data. First, the sample of paired XY data is a simple random sample of quantitative data. Number 2, visual examination of the scatter plot must confirm that the points approximate a straight line pattern. And third, because results can be strongly affected by outliers, any outliers must be removed if they are known to be errors. The effects of any other outliers should be considered by calculating R with and without the outliers included. Okay, so here is the formula for calculating R. It looks kind of scary, but it's really not that bad. And believe it or not, this formula will be easier to use than the next one I'm going to show you, which I probably won't use at all. This formula that requires you to calculate the z-score for each and every one of your x's and each and every one of your y's. And remember, to calculate a z-score, you need the standard deviation of the sample, okay? So this formula kind of helps you to understand better what the linear correlation coefficient really measures and what it really means, but it's not as easy to use for calculations. All right, and then the rounding rule for linear correlation coefficient, we will round it to 3 decimal places so that its value can be directly compared to critical values when we get into hypothesis testing. All right, and then to use a p-value, just like always, if p is low, the null must go. If P is high, the null will fly. All right. So a low p-value supports the claim of a linear correlation. So normally, and we'll get into this more later, but the claim in a hypothesis test about a linear correlation, or the null hypothesis, is that there is no correlation. Okay. So if we reject the claim that there's no correlation, that means the p-value supports the claim of a linear correlation. On the other hand, a high p-value would not support the claim of a linear correlation. All right, so we're going to be using a new table, table A6, and I will have a link to that table in the description of this video. And that will give us critical values. So if we want to use the critical value approach instead of the p-value approach, we can get those critical values directly from table A6. Okay. All right, again, the value of R is always between -1 and 1 inclusive. If R is plus or minus 1, that indicates that there is a perfect linear relationship. Every single one of those points would lie directly on the line. So that really doesn't happen in any real life examples. If all values of, at least no interesting ones, if all values of either variable are converted to a different scale, the value of R does not change. Imagine X being measured in inches versus X being measured in centimeters. That would not change the value of R. And also the value of R is not affected by the choice of X or Y. So you'll have two different variables called X and Y. It doesn't matter which one you call X or which one you call Y. It will not change the value of R. R measures the strength of a linear relationship. It is not designed to measure the strength of a relationship that is not linear. So if you think back to that picture of the points lying along a parabola, that was actually a perfect quadratic correlation that a single outlier could dramatically affect its value. So we want to be careful with those outliers. All right, so here's an example. The table lists 5 paired data values. Use technology to find the value of the correlation coefficient R for the data. So we'll show you what some different technologies, displays look like: StatDisk, Minitab, and we don't really any of these. I think maybe you've used StatDisk a little bit. You might use a TI-83 or 84 calculator. Okay, so I don't mind if you use that. Just let me know on your written work that that's what you're doing. The value of R will be automatically calculated with software or a calculator. So in this case, what you would do is you would put those two sets of data in your lists on the graphing calculator, and then just find this function on the calculator. Okay, but I don't assume that everybody has a graphing calculator. So we'll do it the old-fashioned way. Okay, so in this example, we're going to calculate the linear correlation coefficient by hand. So they want us to use formula 10-1 to find the value of the linear correlation coefficient R for the 5 pairs of chocolate Nobel data listed in the table. So the context for this example is that there are 5 different countries. The numbers under chocolate is the amount of chocolate consumed by people who live in this country, I believe in kilograms per capita. And then Nobel is the number of Nobel Prize winners from that country. So we want to see if there's a correlation between how much chocolate people eat and how many Nobel Prize winners come from that country. So the value of R is calculated as shown below. We set up a table kind of like how we did for finding the standard deviation. Here, the variable X is used for the chocolate values and the variable Y is used for the Nobel values. Because there are 5 pairs of data, N equals 5. So here are the values of X, here are the values of Y, and then we do an X squared column. 5 squared is 25, 6 squared is 36, 4 squared is 16, et cetera, et cetera. Do the same thing for Y squared. 6 squared is 36, 9 squared is 81, 3 squared is 9. And then finally, we do a column called XY, where we multiply each X by its corresponding Y. 5 times 6 is 30. 6 times 9 is 54. 4 times 3 is 12. 4 times 2 is 8. 5 times 11 is 55. And then we add all those columns together. So the sum of the X's is 24. The sum of the Y's is 31. The sum of the X squareds is 118. The sum of the Y squareds is 251. And the sum of the XY's is 159. So now I've carried that row with the totals in it onto the next slide so you can see what goes where. Again, N is 5 because there are 5 pairs of data. The sum of the XY's is 159. The sum of the X's is 24. The sum of the Y's is 31. On the bottom, notice that these are 2 separate square roots. So in the first one, we do N times the sum of the X squareds, which is 5 times 118. And then we subtract the square of the sum of the X's. So that's 24 squared. We do the same thing with the Y's. And this is definitely something you should try on your calculator. This is one that might be tricky. In the end, you end up with 51 over the square root of 14 times the square root of 294. You'll need to put those 2 square roots in parentheses. And that comes out to 0.795 as the value of R.